Hello everyone, we're going to be talking about section 9.2, which is going to be about measures of variation. So this section contains terms that we haven't really gone over, so here's going to be a list of new terms and their definitions. You may have seen one or two of these definitions at some point, or one or two of these symbols, but we're just going to go over them now so we all have a good idea of what they mean. So the first thing we have there is what's called sigma. This is the capitalized Greek letter sigma, meaning the sum. So this just means that if you see sigma in front of some variable, let's say x, and if x represents the numbers 1, 2, and 3, then what happens is when you take the sum, and when we refer to it, we call the sum, we don't say sigma x, we'll say the sum of x. So that will be 1 plus 2 plus 3 is equal to 6. So it's whatever variables or whatever numbers you have contained within a variable. When you go to take that sum, you're just adding up all the different variables. All right, then next we have the lowercase Greek letter sigma. So this is going to be used in variance and standard deviation when we deal with population. But that's also why when we refer to the sum, we don't call it sigma, since we also use lowercase sigma. And when we refer to lowercase sigma, we call it sigma. So that's kind of the difference there. Then we have mu, which kind of looks like a U with like a tail in front. So that's the Greek letter mu. It stands for the population mean. So when we talk about population, we'll always refer to the mean of a population as mu. And also it's important to remember, we mentioned this in one of our last sections, but the population mean is also just the expected value. So we would say mu is equal to the expected value. Then x bar, or x with that line on top of it, that's always going to refer to the mean. So when we see x bar is equal to something, we're calculating or we're finding the mean, and we would pronounce this as x bar. All right, so these are the terms that we're going to see in this section. All right. So the mean, median, and mode gives us a measure of the central tendency, but it really doesn't tell us anything about the spread of the numbers in the list. So mean, median, mode gives us a really good idea of what number is going to be in the middle of our distribution or the average of our distribution, but it doesn't tell us anything else about the spread of the numbers within that distribution. So first thing we're going to go over is range. So the difference between the largest and smallest number in a sample is called the range. Range is just one example of measure of variation. So an example, the range of the set of numbers 4, 10, 23, 17, 12, and 9, the range is going to be your largest number minus your smallest number. So our largest number in this case is going to be 23. Our smallest number is going to be 4. So we saw for our range, we take 23 minus 4, and that's going to be equal to 19. So we would say that our range of the set of numbers is going to be 19. Now we have variance and standard deviation. So standard deviation is the most useful measure of variation, but we have to find the deviations from the mean first, or the differences found by subtracting the mean from each number in a sample. So standard deviation, we're actually going to get much deeper into a little bit later on. We have to kind of build up to standard deviation. So first we're really going to go over deviations from the mean, then we're going to go over variance, and then we can talk about standard deviation. So first things first, we have a first example here, and we want to find the deviations from the mean for the numbers. So we have a set of numbers here. We have 31, 42, 47, 51, and 54. So what we need to do is find the mean of these numbers. So we know how to calculate the mean. We just know it's the sum of all the variable or all the values that we have here in the set of list of numbers, or our list of numbers, and then we divide by the number of numbers. So remember now, ooh, wrong color. Remember now that when we talk about mean, we're going to write x bar instead of the word mean. So we can say x bar is equal to, we have 31 plus 42 plus 47 plus 51 plus 54. And then we're going to divide by our number of numbers, which is going to be 5. We see there's 5 numbers in this list because we have 31, 42, 47, 51, and 54. So then we divide by 5. So now we just get to add up these numbers and divide by 5. So if we do that, we're going to get 225 divided by 5. Now we can obviously tell this is going to simplify to an even number, and it's going to be 45. So now we know that our mean is 45, or our x bar is 45. So to find the deviations from the mean of each one of our numbers, what we're going to do is take the number that we have from our list and subtract the mean. You're always subtracting the mean from whatever number you have. It's not whichever is largest, because we want to know if it's negative or if it's positive. So for our first number here, we have 31. So to find our deviation, we're just going to take 31 minus the mean. So this is going to be 31 minus 45. This is going to give us negative 14. Let's rewrite it just a little bit. So you can say 31 minus 45 is negative 14. Now we want to do our second value, which is going to be 42. So now we take 42 minus 45. This is going to be negative 3. Then we take 47 minus 45, and that's going to be positive 2. Then we can do the same thing, 51 minus 45, it's going to be positive 6, that 2 is weird. And then we're going to take 54 minus 45, it's going to be positive 9. So we found all of these deviations from our mean. So we see here that 31 is going to be negative 14, or 14 less than our mean. 42 is negative 3, or 3 less than our mean. 47 is 2, or 2 greater than our mean. 51 is 6, or 6 greater than our mean. 54 is 9, or 9 greater than the mean. So we found all of these deviations. To check if it's right, what we can do is add all of our deviations together, and if it equals 0, then it's correct. So we would say to check, the sum of the deviations should always equal 0. So we take negative 14 plus negative 3 plus 2 plus 6 plus 9. And when we add all these values up, we're going to get 0. So we know that this is correct. All right. So that's how we find our deviations from our mean. And this is going to be very much a key factor in finding our variance and our standard deviations. Come on, there we go. All right. So to find a measure of variation, it's really tempting to use the mean of the deviations. So if we want to find the mean of the deviations, we know we would just add all these up and then divide by our number of numbers. But we know that this number is always going to be equal to 0, because when you add your deviations up, it's going to be equal to 0. So we can't take the mean of the deviations, or else we would just always get 0. So instead, what we do is we square each deviation, and then we take the mean, except we use n minus 1 in the denominator instead of n. N just meaning that if we had 5 numbers in our list, we're going to divide our sum of our numbers by 5 minus 1. So we see here, using example 1, we have the same values here. We have negative 14 squared plus negative 3 squared plus 2 squared plus 6 squared plus 9 squared. And this is going to be divided by 5 minus 1. Since we had 5 numbers, we're now doing 5 minus 1 in our denominator. So when we find these values, it's going to be 196 plus 9 plus 4 plus 36 plus 81, all divided by 4. So this is going to be 326 divided by 4, or about 81.5. So in this case, 81.5 is called the variance of the sample. This is going to be represented as an S squared at all times, since it's averaging the list of squares. So whenever you think about the variance, wrong word. So whenever you think about the variance, it's always going to be squared. It's going to be S squared, or you can also see it as sigma squared for thinking about a population. So whenever you think about variance, it's always squared. So now we have our definition. And it is important to note at this point that these definitions are different than the definitions in your book. So if you go and look at your book, the definitions will be slightly different. They are equal. They have been proven to work the same, but I feel that these definitions are easier to understand than the ones in the book. So we see here that we have the variance, definition of variance. So the variance of a sample of n numbers, x1, x2, all the way to x sub n, with mean x bar is s squared, so the variance, is equal to the sum of x minus x bar squared divided by n minus 1. Now, this looks a little strange, but we have the sum here, and this just means that we're taking the sum of all of our deviations squared. It's the exact same thing that we did in this example here. So that's what this definition is, this right here. See, we found all of our deviations from our means of our numbers, and then we went and we squared each of them and we added them all together and divided them by n minus 1. And that gave us a number, which is our variance. So that is this equation here. This sum just means that you're taking every value of x in your list, and then you're subtracting that mean from it to find that deviation, and you're squaring it, adding them all up, dividing by n minus 1. All right, so since variance is in squared units, we take the square root of it to get in the same units as the original data. Since we squared all of these values, and since we always refer to variance as s squared, what we really want is to have s, not s squared, because we want these not to be squared terms anymore, because our original list of data was not in squared terms. So we would call the result of this the standard deviation. So this is the standard deviation. We have the standard deviation of a sample of n numbers, x sub 1, x sub 2, all the way to x sub n, with mean x bar is s is equal to the square root of s squared. That is also going to be equal to the square root of the sum of x minus x bar squared divided by n minus 1. Notice this is just the square root of the variance. So when you're working out problems, you're normally going to have to find the variance in the first place. So once you find the variance, you don't really have to plug everything back into this equation. You just need to take the square roots of that value. All right, so let's do an example. Let's put some of this into practice. We see here that we want to find the standard deviation of the numbers, which are 7, 11, 13, 18, 22, 23, and 25. So when we're trying to find our standard deviation of our numbers, we're given our list of numbers, first thing we always want to do is solve for the mean. So let's solve for the mean. We know our mean is going to be x bar. We have all of our values here. We know it's going to be 7 plus 11 plus 13 plus 18 plus 22 plus 23 plus 25. And this is divided by our number of numbers, which is going to end up being 7. We add all these values together. We get 119 divided by 7, which is 17. So our mean is 17. So when we go to find our deviation, remember we're taking, zoom in a little bit, we're taking our number, this is that value of x minus x bar. So when we find our deviation here, we're going to take 7 minus 17. 7 minus 17 is going to be negative 10. Then we have 11 minus 17. It's going to be negative 6. 13 minus 17. It's going to be negative 4. 18 minus 17. It's going to be 1. 22 minus 17. It's going to be 5. 23 minus 17 is going to be 6. And 25 minus 17 is going to be 8. So we have our list of deviations now. Now that we have this, we really want to find our standard deviation. That is our end goal. But the middle step here is that we have to find the variance, because we can find the variance and then we can just take the square root of the variance. We can definitely calculate our standard deviation straight from these values using our equation here, but it's going to get really messy and it's going to be a lot of calculations. So it's much easier to just solve for the variance and then you go ahead and take the square root to find the standard deviation. So let's find the variance first. So we want to find the variance first. So we have s squared is going to be equal to, and remember now, it's the square of all the deviations. So we're going to take negative 10 squared plus negative 6 squared plus negative 4 squared plus 1 squared plus 5 squared plus 6 squared plus 8 squared. And we're dividing by n minus 1. And in this case, we see that n is going to be 7. We can write this up here. N is equal to 7. We also see n here. So we put my little arrow, we say this is n. So we have 7 minus 1. Now we want to solve all of these values. When we do that, we're going to end up with 100 plus 36 plus 16 plus 1 plus 25 plus 36 plus 64. All divided by 6 because of 7 minus 1. Now we can just add all of these values together and solve. So we end up getting 278 divided by 6. So now we have this value and we can calculate what our variance is. So we can just solve for 278 divided by 6, and this is going to end up being 46.3. So we see that s squared is equal to 46.3. So now we want to solve for the standard deviation, which is just s. So now solve for standard, move this over, deviation. So s, we know, is just the square root of s squared, and we know that s squared is equal to 46.3. So this is the square root of 46.3. Now we find this value, what we end up finding is 6.8. So we can say our standard deviation is 6.8. And your standard deviation is always just going to be a value. There's no units to it, it's just a number. All right, so here's a word of caution. So be careful to divide by n minus 1, not n, when calculating the standard deviation of a sample. Many calculators are equipped with statistical keys that compute the variance and standard deviation. Some of these calculators use n minus 1 and others use n for these computations. Some may have keys for both. Check your calculator's instruction book before using any statistical calculator for the exercises. So just make sure that if you use a graphing calculator or really any calculator that has statistical keys on it, that you know if you're dividing by n or n minus 1, if you're able to find standard deviation. I'm going to zoom in here. So for example, if you have a TI-84 plus C calculator, this is how you would find the standard deviation. So the data entered into the L sub 1 list on the TI-84 plus C calculator. Figure 4 shows how the variance standard deviation are then calculated through the list-math menu. Figure 5 shows an alternative method going through the stat menu, which calculates the mean standard deviation using both n minus 1, indicated by Sx, and n indicated by sigma x in the denominator and other statistics. So you can calculate your standard deviation just straight out from a calculator if you have one that is able to do it. All right, so the variance and standard deviation are also random variables. We're going to talk about what random variables are. Remember, we have these values in X, and we assign them numbers, usually 1, 2, 3, something along those lines. So we have random variables. We refer to variance and standard deviation of a random sample as the sample variance and the sample standard deviation. In the last section, we mentioned that the expected value, E of x, is the population mean, mu, which is what we mentioned at the very beginning of this lecture in our definitions. So when measuring a population, we also use the population variance and the population standard deviation. These equations are essentially the same. The only thing that we change is what we call it by. So instead of S, or instead of S squared for our variance, we have our population variance. It's denoted as sigma squared and is defined as sigma squared is equal to the expected value of x minus mu squared. The population standard deviation is denoted as sigma, since it's just the square root of sigma squared. So once you find the variance, you just take the square root. All right, for data in a grouped frequency distribution, we want to use this definition. So we have standard deviation for a grouped distribution. Remember that these are usually our tables. We see intervals instead of actual values, and then they have frequencies. So the standard deviation for a distribution with mean x bar, where x is an interval midpoint with frequency f, and where n is equal to the sum of f. This is just the sum of the frequencies. So when you have your intervals, you always get a listed frequencies of how many times a number in this interval appears. So our sigma f is just the sum of our frequencies. So when we divide, or in our denominator in this equation, so instead of our number of numbers, since we have intervals, we don't exactly know how many numbers of numbers, we're just going to take our sum of our frequency minus 1. And we'll go over this in our next examples. So we see the standard deviation for a distribution with mean x bar, where x is an interval midpoint with frequency f, and where n is equal to the sum of f, sum of frequencies, is s is equal to the square root of the sum of x minus x bar squared times f, so times the frequency, divided by n minus 1. So this is pretty much almost the exact same definition that we had for standard deviation, not in a grouped distribution. The difference now is that n is the sum of frequencies, and we're also going to multiply our frequency for each one of our intervals. And when we choose our interval, we choose a midpoint. So for example, we're going to go into example 3 here, which is going to be your turn number 2. And we want to find the standard deviation for the following grouped frequency distribution. So we see our intervals here are from 0 to 6, 7 to 13, 14 to 20, 21 to 27, 28 to 34, 35 to 41, and that would be all. Now we have our frequencies. So we're given our intervals, we have our frequencies. Now remember, we're using our midpoint, just like how we normally did certain things here with our last section when we had frequency distributions. We always picked a midpoint as kind of the average of this interval. So if we're picking our midpoint between 0 and 6, our midpoint here is going to be 3. Remember, you find your midpoint by taking the second number minus the first and dividing by 2. And that's how you find your midpoint. So we can do the same thing for the second, and we end up getting our midpoint is 10. Then on our next one, we get 17. If we notice a pattern, our midpoint is increasing by 7, and that's because our intervals are in 7s. So we see that our next value is going to be 24, and we have 31, and 38. Now, our next column here is going to be our deviation from the mean. This is that x minus x bar. So, and remember, we're taking our midpoint, and we have these midpoints here, but we don't have an x bar. We don't have a mean yet. So, to find the mean, we need to use the definition for mean in a grouped distribution. And remember, we had this definition in our last section, but if you happen to forget, the definition is our mean is equal to x times f, or the sum of x plus f divided by our number of numbers, which is going to be n. So this is just to say we take our midpoint, we multiply by our frequency. We do this for each one of our midpoints, and we divide by our number of numbers. So we want x bar, move this down a little bit, x bar. So our first midpoint is going to be 3, and the frequency is 2, so we have 3 times 2. Then for our second point here, our midpoint is 10, and our frequency is 4, so we have 10 times 4, plus then we have 17 times 7, and 24 times 10, 31 times 3, and 38 times 1. And then we divide this by our, another little mess up. So our denominator is the sum of frequencies. We do refer to this as n, but we want to add up the sum of our frequencies here in our table. So when we add up these frequencies, we're going to end up getting the value of 27. And we're just adding these up, so we're just saying 2 plus 4 plus 7 plus 10 plus 3 plus 1. So we get the sum of our frequencies is just 27, and that's what we're dividing by. Because our number of frequencies, this is actually telling us how many numbers are going to be in our list, because we know that in these intervals, the numbers are showing up this many times. So we have our value of 27. Now we can just solve for x bar. So when we add these, when we multiply these singular values, we get 6 plus 40 plus 119 plus 240 plus 93 plus 38. This is all divided by 27. Now we can find this value. We end up getting 19.85. So our variance isn't always going to be a nice whole number. Sometimes we are going to get a decimal. So in this case, we do the exact same things as before, except now we have a decimal, so the numbers we end up getting are going to also have decimals. So we have our mean here. We want to find our first column here, just our deviation from the mean. We can write our mean up here so we know what it is. We don't have to keep scrolling back and forth. We got 19.85. So we can fill in our first column here. Remember, we're using our midpoint as x. So we're taking 3 minus 19.85. I'm going to write it above. These columns are not big enough. So remember, this is x for our midpoint minus 19.85. So for our first point here, we're taking 3 minus 19.85. It's going to give us negative 16.85. Then for our second, we're taking 10 minus 19.85. It's going to give us negative 9.85. Then we take 17 minus 19.85. This gives us negative 2.85. Now we're taking 24 minus 19.85. It's going to give us 4.15. So we kind of see here that once we switch from a number that is less than the mean and then a number that is greater than the mean, the decimal is going to end up changing. Then we take 31 minus 19.85. It's going to be 11.15. Then we want to take 38 minus 19.85. It's going to be 18.15. So now we have our deviations. Now remember, we want to take the square of our deviations. So it's going to be x minus 19.85 squared. So it's just going to be this value in the column we see with just the deviations, and we're just going to square these numbers. So as an example, this first one here is going to be negative 16.85 squared. This number is going to be large because they're decimals, so I'm going to have to erase this. But if we square negative 16.85, we get 283.9225. We want to keep a good amount of decimals, so I always suggest 3 or 4 decimals, because if we round too much, our final answer is not going to be correct because we've rounded too many times. So it's important to keep a good number of decimals in this case, so we're getting an accurate answer. So then we want to square negative 9.85. When we do this, we're going to get 97.0225. Then we're going to square negative 2.85. That's going to be 8.1225. Then we want to square 4.15, which is going to be 17.2225. Then we're going to square 11.15, which is going to be 124.3225. And then we're going to square 18.15. And this is going to give us 329.4225. So now we have the square of our deviation from the mean. Now that we have these values, we are just so close. We're like one step away from finally being able to calculate our variance. So now what we're doing is we're taking this value that we found from squaring the deviation from the mean, and we're going to multiply it by the frequency of our interval. So in this case now, we're taking x minus 19.85, which was squared, and we're multiplying it by our frequency, which is f. So in the first case here, we're going to take 283.9225, and we're multiplying it by 2. Once again, this number is going to be longer, so I'm going to erase this and write the value. So when we multiply these together, we're going to get 567.845. Now for our second interval here, we see we have 97.0225, and we're multiplying this by 4, because that's our frequency. When we do that, we're going to get 388.09. Then for our third interval, we have 8.1225, and then we're multiplying this by our frequency, which is going to be 7. When we do this, it's going to give us 56.8575. Then we can take our next interval, which is 17.2225, and we're going to multiply it by our frequency, which is going to be 10. So this is going to give us 172.225. Then we take our fifth interval, which is 124.3225, multiply it by our frequency, which is 3. When we do this, we end up getting 372.9675. Then our last interval here, we have 35 to 41. Our frequency is 1, and the square of our deviation was 329.4225. We're just multiplying by 1, so it's going to be the same value, 329.4225. All right, so we've found all of these numbers. Now we just want to add them up. We want to take the sum. So when we say the sum, remember we're adding each one of these variables. So we can write this over here. We can say, this in parentheses, our sum of x minus x bar squared times f squared is going to be 567.845 plus 388.09 plus 56.8575. And I'm going to continue this in the next line, so I'm not like going back and forth. We have 172.225 plus 372.9675. And lastly, we have 329.4225. And remember, this is our sum. And then it's going to give us a value. I'm going to put a bracket around this instead. So when we add all of these values up, we're going to end up getting 1,807.4075. So that's our sum. So we can write this down here as well. 1,887.4075. So this is the sum of the squares of our deviations times our frequencies. So remember, for our standard deviation for a group distribution, we found our numerator. See here, we have our numerator here, and we found this value. So making this chart can be really helpful when doing problems like this, because it really takes you step by step on what you should be doing, and then finally it gives you your numerator. So we can say now we can solve for our standard deviation. We know our standard deviation is going to be S is equal to the square root of the sum of x minus x bar squared times f divided by n minus 1. We determined in this problem that n was equal to 27. That was the sum of our frequencies. We know what our numerator is because we solved for it here. So we can write in our numerator. We know that this is going to be the square root of 1,887.4075 divided by 27 minus 1. So we simplify this just a little bit. We know this is going to be dividing by 76, 26. Now we can calculate this value, and we end up getting a value of 8.52. So we can say as our final answer, the standard deviation is 8.52. All right, so we found a standard deviation for grouped frequency distributions. We found standard deviations for regular distributions. So now we know how to find a standard deviation. A word of caution here, so in calculating the standard deviation for either grouped or ungrouped distributions, using a rounded value for the mean may produce an inaccurate value. So this is what we mentioned before with keeping a certain number of decimal points. You always want to have that 3 or 4 decimal points so you can get an accurate reading, especially when it comes to the mean. You always want an accurate value of the mean. All right, and this is going to be our last example here. These examples are a little bit tedious. They take a while to actually write out. So we're going to have our last example, and this is going to be a more application-based example. So we have here home-based workers. So because of advancements in communication and information technologies, workers are increasingly able to work at home. The following grouped frequency distribution gives the number in millions of employed people who work at home for various age groups in 2010. Assume the midpoint for the last interval is 69.5. So we have here our grouped frequency distribution. Thankfully, this problem already gives us our midpoint, so we don't have to find our midpoint, but we will have to do everything else. So we have our age here. We have 15 to 24, 25 to 34, 35 to 44, 45 to 54, 55 to 64, and then we have anyone over the age of 65. Then we have our midpoint here, so this is going to be the value in the middle. And then we have our frequency. So our frequencies in this case are not going to be, are not whole numbers. They're actually just decimals in this case. But for part A, we want to find the mean age of employed people who work at home. And then for part B, we want to find the standard deviation for the data. So for part A, we're just finding the mean. So just like we did before in example 3 when we found our mean, we took the mean for a grouped frequency distribution. So we'll need to do the same thing here. So we can say, we use the definition of the mean for a grouped frequency distribution. And remember, that's going to be x bar is equal to the sum of x times f. We'll write this more off to the side so it's not so crunched in. x bar is equal to the sum of x times f. And remember, this is the sum of x times f. And then we have our denominator. And our official definition is written as n, and then we say where n is equal to the sum of the frequencies. All right. So we have our midpoints, so we don't have to find those. But to find the mean, remember we take the midpoint, multiply by the frequency. So for our first term here, for our first interval, we're going to take our midpoint, which is 19.5, multiply by the frequency, which is 0.4. Then our second interval, our midpoint is 29.5, multiplied by the frequency, which is 1.3. Third interval, we have 39.5 times our frequency, which is 2.1. And let's scoot over just a little bit. And we see our next interval is going to be 49.5 times the frequency, which is 2.5. We're going to have to scoot over a lot of it. Our next one is 59.5 times our frequency of 2. So 59.5 times 2. Then we have our last interval, which is going to be 69.5 times 1. All right, and then we want to divide by the sum of our frequencies. So we'll need to add up all of our frequencies. So you can zoom in a little bit here. Sum of our frequencies. We add all these values up, and we're going to end up getting 9.3. So our denominator here and our mean is going to be 9.3. Now we just want to add all of these values up. And you can plug this straight into a calculator. And if you do, you should end up getting that x bar is going to be 47.457. So it's very tempting to round up to 47.5 because at least we'll just have one decimal. Kind of makes sense with the table that we have here. But remember, in our caution, when we calculate our standard deviation for either grouped or ungrouped distribution using a rounded value, for the mean may produce an inaccurate value. So we want to keep our number here. You can round. If you can avoid rounding by using a calculator, then definitely always do that. But if you do have to round, make it to the third or fourth decimal. In this case, our fourth decimal was 0, and it wouldn't have been rounded up, so we just left it as 47.457. All right, so we have our mean. So we finished part A. Now for part B, we want to find our standard deviation for the data. So we're going to be doing the same thing as we've done in the last two problems, but now our mean is definitely going to be a little bit more annoying when we calculate it since it has 3 decimal points. But we have the same exact values here. So remember here we have, this is going to be x minus 47.457. Then this is going to be x minus 47.457 squared. And then this will be x minus 47.457 squared times your frequency. All right, so remember our first midpoint is going to be 19.5. Let me scoot this over just a little bit. So we know this is 19.5. This is going to be 29.5, 39.5, 49.5, 59.5, and 69.5. All right, so these are our midpoints that we're using. Now remember, we're going to take our point minus our mean. So in our first column, in our first row, we have 19.5 minus 47.457. So when we find this value, it's going to be negative 27.957. Then we're going to take 29.5 minus 47.457, and we're going to end up getting negative 17.957. Then we take 39.5 minus 47.457. This is going to be negative 7.957. If you recognize here, these values just decrease by a factor of 10 since our midpoints are increasing by a factor of 10. Then, sorry, they are increasing. Then we see here that we have 49.5 minus 47.457. This is going to give us 2.043. Then we have 59.5 minus 47.457. This is going to give us 12.043. And then we have 69.5 minus 47.457. This is going to give us 22.043. So once again, we see here that it is increasing by a factor of 10 since our midpoints are increasing by a factor of 10. All right, so now we've found our deviations from our mean. For our second column, we're just going to be squaring these numbers. So in our first column, we'll take 27.957 and we'll square it. And obviously there's no room. So that's what we're going to be doing. We end up getting 781.594. Then when we square negative 17.957, we're going to get 322.454. Then we're going to square negative 7.957, and that is going to give us 63.314. Then we're going to square 2.043. That will give us 4.174. Then we'll square 12.043. This gives us 145.034. And then we'll square 22.043. And that's going to give us 485.894. All right, so now we found all of our squares. Now we want to take this value of our squared value from our mean, or our deviations from our mean, and we're going to multiply by our frequency. So, all right, the frequency over here. So remember, our frequency for 19.5 was 0.4. Our frequency for 29.5 was 1.3. Our frequency for 39.5 was 2.1. Our frequency for 49.5 was 2.5. Our frequency for 59.5 was just 2. And our frequency for 69.5 was 1. So now we want to take our values in our second column and multiply by our frequency. So we'll take 781.594, and we're going to multiply it by 0.4. When we do this, this value is going to be 312.6376. Then we'll do the same thing for our second row here. We'll take 322.454, multiply by 1.3. It's going to be 4.19.1902. Then for our third row, we'll take 63.314, multiply by 2.1. It's going to give us 132.9594. Then we'll take 4.174, multiply by 2.5. This will give us 10.435. Then we'll take 145.034 multiplied by 2. It's going to give us 290 and 68.068. Then we have 484.894 multiplied by 1, so it's the same value. All right, so now we have all these values. We have the deviations from the mean squared times our frequency. And now remember, we want to find the sum of all of these values. So we're going to add all of these values up. So remember, we have our sum, our sum of x minus x bar squared times f is equal to, and we're going to add these numbers up. So we have 312.6376 plus 419.1902 plus 132.9594. And we're going to go to the second row here. Then we have 10.435 plus 290.068 plus 485.894. When we add all these values up, we're going to get 1,651.1842. Now we can write this in our sum here. We have 1,651.1842. And we know our standard deviation. So now we can solve for the standard deviation. We know our standard deviation is the square root of the sum of x minus x bar squared times f divided by n minus 1. We know our value of n, it's going to be 9.3. We know our numerator. Since we just solved for it, we know this is 1,651.1842 divided by 9.3 minus 1. So when we rewrite this, to simplify our denominator, it's going to be 8.33. And when we solve this, we should get a value of about 14.1. Now we can drag this out to more decimal points if it asks, but we did see that when we calculated this, it should be 14.1. That's going to end up being 1045. So that is the whole number, but it just depends on the question if it asks you how many decimal points to round to. All right, so we have gone through how to solve for our standard deviation, which we said before, this is our most useful measure of variance. So we're going to be solving for the standard deviation a lot within this section and the next section. So as always, if you have any questions or concerns, you can always send me an email, pop into my office hours, or you can submit an anonymous question to our anonymous question form. All right, I will see you all virtually later.